What we will be taking a look at here is the multiplication rule as well as tree diagrams. So if you recall, there were some axioms that we went over previously, and the axioms of properties of probability, they don't contain an explicit formula for calculating the intersection of events. However, if you take a look at this proposition that we've talked about before, it does contain implicitly the formula, and that formula would be the probability of A intersection B is equal to the probability of A plus the probability of B minus the probability of A union B. So note that this right here that we just now came up with based on that axiom, it requires three pieces of information, right? So it looks like for us it will require the probability of A, the probability of B, and then the probability of A union B. And this is for the calculation of the probability of A intersection B. Recall that conditional probability that we've also covered has the formula, the probability B given A is equal to the probability of A intersection B over the probability of A. So this definition of conditional probability yields the following alternative multiplicative formula that only uses two pieces of information. So now we have the probability of A intersection B is equal to the probability of A times the probability of B given A. We go to our example. Our example states that two consecutive traffic lights have been synchronized to make a run of green lights more likely. So in particular, if a driver finds the first light to be red, the second light will be green with probability 0.9. And if the first light is green, the second will be green with probability 0.7. If the probability of finding the first light green is 0.6, we are to find the probability that a driver will find both lights green. All right, so let's let A denote the event that the first light is green. Right? First light is green for us. And B can be the corresponding event for the second light. So B is the corresponding event for the second light. So the question concerns the probability of the intersection of A and B. Okay, again, the question concerns the probability of the intersection of A and B. So from the multiplication rule, we get, and this is from the intersection, the probability of A times the probability of B given A. So for us, that's going to just simply be 0.6 times 0.7, which is 0.42. So this multiplicative formula that I have here, this multiplicative formula generalizes to more than two events. As you can see, it's the probability of A intersection B intersection C. So that's going to be the probability of A times the probability of B given A times the probability of C given A union B. So the multiplication rule for 3 events is what we have. So our example here says to pick 3 cards from a deck, find the probability that the first draw is an ace, the second draw is a king, and the third draw is a queen. Alright, so for a solution, let's go ahead and let A equal the first draw results in an ace. Okay, and then let's let B equal that the second draw results in a king. And then C, event C can be that the third draw results in a queen. Alright, so we have events A, B, and C. A is the first, results in an ace. B is the second draw, results in a king. And C is the third draw, results in a queen. So therefore, we want to calculate probability of A intersection B intersection C. So from the multiplication rule, we get the probability of A times the probability of B given A times the probability of C given A intersection B. Alright, so what does that leave us as far as inputting values? Well, it's going to be 4 out of 52. And now the probability of B given A has already occurred. That makes it times 4 out of 51. And then the probability of C, the third one being a queen, giving that we have the intersection of A and B. That'll be 4 out of 50. Thus, our calculation from those 3 products give us 0.000483 is what I have. Here's our next situation. Of the customers entering a department store, 30% are men and 70% are women. The probability a male shopper will spend more than $50 is 0.4, and the corresponding probability for a female shopper is 0.6. The probability that at least one of the items purchased is returned is 0.1 for male shoppers and 0.15 for female shoppers. So our task is to find the probability that the next customer to enter the department store is a woman who will spend more than $50 on items that will not be returned. Alright, so let's take a look at this. So let's let W, our event W, let that be that the customer is a woman. Alright, and let's let B be that the customer spends more than $50. Spends greater than 50 bucks. Let's label R. R can be that at least one of the purchased items is returned. At least one of the purchased items is returned. All right. So what do we want? We want the probability of the intersection right? We want the probability of the intersection of W, B, and R complement. We want the probability of the intersection of W, B, and R complement. Okay, so by the formula that we talked about earlier, we can write for our specific problem W intersection B intersection R complement, right? So if that's the case, then according to the formula, then we need to calculate the probability of W times the probability of B given W times the probability of R complement given W intersection B. Okay, so now just inputting our values, we get 0.7 times 0.6 times 0.85. Let's see, let me crunch the numbers. Calculator, I get 0.357. 0.357.